is. So I will hope you enjoy the night, get some more knowledge, and yeah, to enjoy the drink afterwards, of course.
Hello to everyone. Yes, first, I'm sorry, I have to talk a little bit about Anchorman. It's mandatory, and then we can go directly to the we can go directly to the stuff that I think that we like both, all of us. So yes, who we are. We were founded in 2000, a long time ago, if you see, but the starters were more like a software-based company, and then at some point they have a really clever idea and to move to big data. I think that we were one of the first in moving to this area, and then that's the reason we are here. So we are based in the Netherlands. We have two main offices, although we have another third, which is a little bit smaller. It's in, but the bigger ones are in Amsterdam and Groningen. We are more than 80 people dedicated to engineering and data science. And yes, a lot of good stuff here. So yes, what we offer? A lot of things. So the first big data services. So as I told you, our or the beginning of the company was big data and software engineering. So actually, our main expertise is big data engineering. That's the reason that we have big data services almost from the beginning. Then we design architectures, implementations, platforms, whatever you like. We have it. Also, we moved to data platform. So what we want to do is not only give the architecture itself, but focus also on large scale database. So as I told you, not only the hardware itself, but also to have something to say in the platforms. And then my part, this is data science and artificial intelligence, where we have really nice people. Yeah, we are a team of almost 15 people, and we have built a lot of things. Recommendation systems, chatbots, predictive maintenance, we have personal text mining, time series analysis, forecasting, so many things. It's so great. Actually, I never get bored here. It's one of the best things of my job. And computer vision, and as well, so really nice. And the high potential program, which we're going to change the name, is going to be Anchorman Academy, but at the end, it's something that might be interesting for some candidates, because what we have is two ways, let's say. One is that our customers, we provide them with people that want to be specialized in this area, big data, engineering, or data science, and then they will be in the offices 4 days per week, but one day we will capture them, and then we will retain here to to teach some big data things, and then yes, it's really nice education. I think so, because we're giving it, so I cannot say anything else. And also we have our own trainees program, and then it's for Anchorman, so candidates can come to us, and then they stay here for 2 years, and then they can make both. So they can be experts in data science and experts in data engineering, which in my humble opinion will be the future. So because a combination or a hybrid model between data science and engineering, at least I have seen it a lot, or it's requested a lot by companies. You should domain a little bit of both things. Cool. Let's move on. Yes, a lot of customers. No need. So, who am I? As I told you, I'm the head of data science. My background can be a little bit strange for you because I'm a biochemist. A long time ago, I did biochemistry, even a PhD, so a really, really long time ago. And but at some point, I really decided to specialize in omics technologies, which are a lot of data, and then intensive analysis, anomaly detection, and the last years in Kubernetes. I'm a certified Kubernetes administrator, which is not too much, but it took me a while to get it. Then today I want to introduce you first. Why are you here? Why the hell do you come to so far in the Amsterdam? And then I hope that you're here because of this motivation. Then we're going to we're going to say the problem that we have and the solution that we think that might be important. I'm going to introduce you into the continuous integration, continuous development or deployment pipelines, some workflows that we have prepared for a simple example, and next steps that we would like to proceed after that. So why are you here? Come on, guys. I hope that this is for this. You see here, this is the interest over time. So Docker, amazing. Docker was an existent in the 4 years ago, and look at the blue line. Amazing, eh? It's growing exponentially. So if you don't know what Docker is, you should, in any case. That's the future. Docker is here to stay. But also the rest. So if you see GPUs are getting, it's more linear because GPUs always has been interesting. That's it. So it's not a problem there. Yes? Okay, sorry. Docker? Yes, very nice question. I really enjoy this question. Okay, do you know what a virtual machine is? Yes, it's a virtual machine. Then imagine that you have to configure by yourself. Have you done it? Install some packages. If it's Linux, yes, it's a pain in the ass to go there. Sudo apt. Oh my goodness, everything the same. Yeah, I'm a data scientist, if you noticed. So really, for me, it's really hard. With Docker, what you can do is automate. Because at the end, when you construct, is a container. That's the reason of the Docker, where you tell to Docker program, hey, I want to start from Ubuntu, okay, from Linux, and then I want to install this and this and this and this, everything. And at the end, what you get is some kind of zipped file with everything installed. And then you can run this everywhere. The only thing that you need is Docker. Yes? Clear enough? So the point of Docker, or Dockerizing, which is almost, is even a verb, is to really containerize your environment. So you control your environment from the beginning to the end. You know that you start with Ubuntu, and then you know which library have you installed, which R version have you installed, everything, from the beginning to the end. That's the reason it's so famous, or that's because you control every single detail or your environment. If you have played with Python environments, have you played with them? Yes, but this is a higher level. Because Python, you can control the packages that you install, but no, you cannot control the Linux dependencies that you have to install. With Docker, you can. Yes? I hope that is informative enough. And Kubernetes, what is Kubernetes? I will explain later. But also you will see that it's growing exponentially. So really, and DevOps. DevOps is, so imagine, I think that I read in the newspaper that, yes, machine learning, big data is really a hype. Now for hiring people, this is the next hype, DevOps. So now DevOps specialists, well. So first, Kubernetes. This is a thing from January 4th. You can see it's the red bar. So everybody's asking for Kubernetes. It's the new hype. So you can see there, but it's amazing how fast this thing grows. But even compared with TensorFlow, which is another hype with GPU, we will see later, but it's really high. So yes, Kubernetes will dominate. DevOps, amazing. DevOps skills, source. We are looking DevOps engineers everywhere. New Linux Foundation, the man of high DevOps, DevOps is going so far. So that's the reason I hope that you are here. Because we are going to talk about this. DevOps, one part continuous integration, continuous deployment, and Kubernetes, and how to integrate everything together. Okay? Yes, let's define the problem. GPUs. Why GPUs are so important now, or at least in the data science world, because GPUs, they have been there for a long time. But why they are so important? The reason is that, and you have seen it, I have a computer at home that I think for the last 10 years, I don't have to change my computer. CPUs are in a saturation thing, then the speed is not growing so fast. But I remember 15 years ago where you have to buy a computer almost every year, or 2 years, not anymore. So CPUs, are really getting into a standard, let's say, speed, and by physical limitations, we cannot grow more by CPUs. However, and that's the point of and this is the Moore's law. So every 10 years, you double the speed of the processor. Yeah, it's not applicable anymore. However, we have CPUs. And I must say, yeah, the source is NVIDIA, so yeah. And then they think that 1,000 by 2025. Okay, whatever. But you see the point. So CPUs are important just because CPUs, they cannot be faster. That's it. But GPUs, they can't be faster. Okay? And that's the main reason. Yes, again, another thing. So 2018 will be the year of the GPU accelerating everything. And yes, Spark, we were there. Really nice in Munich with the NVIDIA founder, and then they say, yes, we're going to accelerate everything. We're going to put an NVIDIA chip everywhere. So the reason why you can understand it. So crypto mining is not so, let's say that you don't need so many GPUs anymore for crypto mining. They need another market. And this is us. This is data science. And then the reason, and then behind it, then the point is that they're going to invest in these years a lot of money to get data science into GPUs. So you can expect that from NVIDIA. And then also they develop Rapids, which is because the limit is again. So when you have a computer, CPU, GPU, then there is a limit. It's the unit itself. When you want more, at the end you have to parallelize. You have to divide your processing into 2, 3, or more nodes. That's what they are investing to as well. So 2 parallelized GPU worlds. And then they develop Rapids, really nice, based on Python. So directly in theory, you can write your Python code, normal Python code, and then you can run in parallel. Good, really nice. But where is the problem really? Or at least if you have played a little bit with GPUs, and we have almost today, the problem is this. My goodness, drivers. So really, I'm sorry for the word, but they're really a pain in the ass. But really, So yes, version of this. Oh, is this the newest version? My goodness, this is really. And they're chaotic. They put the new drivers every time. Oh, it's really hard. I'm telling you, and it's really hard from a long time ago. Because I remember to install my driver from my NVIDIA graphic card, and it was the same for years. Drivers are always the problem with GPUs, always. And even an additional problem, or not problem, let's say, that they discovered magically that changing the software, so it's the same, if you see here, is the same hardware, so the same graphic card, you can increase by 2, so duplicate your speed just by changing your software. Unbelievable. Why the hell they didn't find out this before? This is understandable. So the point is that, and this is the key, you have to, not only drivers are important, but also the point is that in order to get the rhythm of GPUs, you have to update your drivers and all the software that you have also really fast. But really fast, because you can find out that the new version is twice as fast as the one that you have. So they're really hard to install, and you have to install them frequently. Really bad combination. Really, really bad combination. Then what, or at least what do we think that is the solution? So the solution is, or at least for a humble data scientist as I am, is going from code to results. I don't want to care about drivers, to be honest. I don't want to care about installing things. I don't want to care about anything. I just want to be focused on my code, and it should run. That's the solution. So anything in the middle should be automated, period. And you have, as I told you, you can't install drivers automatically. You have to install drivers automatically. You have to update them frequently. So how we do that? We're going to work with this example. I don't know if you like TensorFlow and deep learning. This is the classical SDE, hello world. Anyone knows what is this? It is a data set. Come on, don't be shy. MNIST. Yes, we have a prize. MNIST. So handwritten numbers. We're going to build 2 models, and you will see it how we can process them automatically. So I promise, code, results, nothing in the middle. Clear? Yes? Let's do it. How? Yes, first we need continuous integration, continuous deployment platform. So we choose GitLab, just because from April, yes, this should be something in interim, but yeah. From April, they have an integration with Google Cloud automatically and with Kubernetes. So GitLab can integrate everything. However, because we love to be platform agnostic, you will see that we haven't used their way of doing it, and we have done it manually. But you will see that it's really easy. It's not hard to do it. Yes? Okay, I promised to talk about Kubernetes. So what is Kubernetes? First, you know now what Docker are, okay? But you can imagine that you want more than one computer, because you will have maybe one database or several virtual machines. You want the database, you have also your web application, or you want to get things in parallel, so you need several of them. How do you administrate, how do you deploy it and scale and everything, your Docker images? Kubernetes is the solution. This is designed for automatically deploy, scale, and manage your Docker images. That's what Kubernetes is doing for you. It's designed by Google some years ago, but they released the code, which is something amazing, because they had this technology in their facility, which is a really nice technology, and they opened it to the world. And as I told you, platform agnostic. We can run it everywhere. Everywhere. Azure, Google Cloud, AWS. Now you can't have a Kubernetes cluster with one click. You will see with one command everywhere. It's free itself, so the software, but you pay for the virtual machines that you're using. Yes? Yes. Now it's open. Google charged you a little bit in the past, but now it's free. So you only pay for the virtual machines. And why? As I told you, the main thing is that we can schedule and run application on cluster. But the point is that also, and you will see today, we can automate its creation and deletion. So if I need it only for some days, because I have this model and I want to run it, to train it, maybe it requires some days, but I don't need a cluster for months. I don't like to pay for months. So I will also like to create and delete automatically. Perfect. You can. Multi-platform, I want to insist in that. We have seen that before. It's scalable. So if you, let me see, it's scalable. Imagine that you have some virtual machine with Kubernetes, and then suddenly you realize that you need twice, 5 times. You can scale. You can buy more virtual machines and add it to the Kubernetes cluster. No problem. And it's CPU compatible, but you will see, I think that this slide is later. Yes? Okay. But you will see that this Google set this up a year ago. So January last year, and not so in the past. So yes, just for me to know, how many of you do you know what is CI/CD? Please raise your hands. Don't be shy. Oh, well, a lot. But for the rest of you that you don't, no worries. We're starting. We're used to it. I will try to enlighten you a little bit. What is continuous integration and continuous delivery or deployment? Both. Sometimes you can use it as synonyms or not. And then which is DevOps. I think that this slide is really nice to know. So that is more or less the pipeline that you should do with when you design code in any language. You have your code, you build, you integrate, okay? Then you test it, okay? Then you release your versions, then you deploy it, and then you operate with it. So if you consider code and build, you have an agile development. So sprints, so on. You know what is that. Now, continuous integration. What you integrate is the tests and the integration itself. So now your code is automatically compiled, but also tested. Perfect. That's continuous integration is meaning that your code is not only there, it's tested, and at least you have some quality measurement that is telling you, hey, at least my code has passed my tests. And this is continuous integration. We will see how we test our code. Then continuous delivery is just to release. So we automatically set released and so on. But what I like most is continuous deployment, because you don't only deliver it, but also put that into production. You put your code working. It's not only that you have a package or a zip file where your version, no. It's really into one location, into one server, and your code is running. That is the difference from continuous delivery to continuous deployment. And DevOps, which also is the operation and how to scale, how to put things up and down. And I want to release my release should have an increased. Some of them currently released that I did a little bit. It's like a canary. So you show a little bit of the canary and then see if it's working or not. Then it's just the DevOps world. Clear? Are you happy with DevOps? You know, this is the next step of software technology, and highly, so DevOps skills are demanded a lot, really a lot. Now, what we're going to do, for real, we're going to integrate this, the continuous integration, and we're going to show you in this way. So first, the code will be pushed into GitLab. I don't know how many times I do that per day, to be honest. I lost my count, so we really pushed a lot. Even though you have seen this comic, and when it's in case of fire, you push and get away. You haven't seen it? No. Okay, it's fine. But yes, pushed, and then this will be the trigger. It will be the trigger. Oops. That tell to GitLab, please launch a runner. A runner is nothing else than a Docker container that will run your test or your code on it, okay? And what you will do automatically is install all the dependencies and run the test. So you will compile your code. This is a language that needs a compilation, and it will test afterwards, okay? If you are in the Java world, you know what is that. So first compile and then test it out. And also we're going to use continuous deployment. So then this code is not only in your file, but also will be put into Kubernetes, and then it will work. So that's how the entire pipeline. In this way, we can achieve the goal that we proposed at the beginning. So code, results. Everything in the middle should be automated. So, okay, this is maybe I missed this, sorry for that. When Kubernetes from Google Cloud Incorporated GPUs, because we're going to make this a little more complicated, because we're going to use not classical CPUs, but cluster with GPUs. And then it's just from February 12th of 2018, almost a year ago, a little bit less than a year ago. So, new thing, GPUs. Then, what you are going to see in the lab, because I'm going to run some things even on here. Let's see if they work. As always, you know what happened with software, but I'm not scared, because if Windows fail, so this can fail. It's not a problem. Then what we're going to do is, we're going to push. In this case, because it's not my computer, I cannot push. I will go for GitLab and trigger directly the pipeline, but it's the same. It's like a push. So imagine that I'm pushing. That's it. Then we're going to test. And then you remember that we're going to use the MNIST. We're going to build a deep learning model, okay? Then we're going to test it, but we're going to test it in CPU. Why, you might say, Angel, why? Because normally, or at least in my opinion, we make a lot of mistakes, small mistakes. Then if it's run in a CPU, and also you check, because it's important to check that your accuracy is increasing, or you are getting lower and lower, really your, now forget it, but it's getting better and better results. Let's say your accuracy is increasing, okay? Then at least you are running for one epoch, okay? Then in this way, you know that your model is working. You don't have any mistakes, so you don't have any typos or something like that, but also that your model is getting better and better, And then, and this is cheap, This is a processor, so even it can run in your computer. It's not a problem. And then if we're happy with the results, they can go for the expensive thing, and then create automatically The server ran 5 epochs, just to show you. We have to do it real time. I cannot. And then, but even deleted. That is really, really nice, in my opinion. Why? Because imagine that you have a model that can run for days, and you forgot it. They are charging you every day that you forgot, but not here. You delete it automatically. Clear? Do you want to see the magic? So for you to know, I'm sorry because sometimes I get really anxious. And this is the model. It's copy-pasted. So it's from the TensorFlow. So we don't put anything fancy here. But if you see what you're going to build some layers, dense layers, and then or drop out, and then we change the activation function here of max, and then we optimize with Adam. And here, if you see, what we have built is not here, but we can play with it in the number of epochs. What we define is a value that you can put into the command line, and then you can set 1 epoch or whatever number of epochs you like. Yes? Okay. By the way, all this material, don't try to copy-paste it. It's already online. I wrote a blog some months ago, and everything is there. Explanations, a detailed explanation show. Don't worry about that. Everything is online, and then you can check. Yes, ncomer.nl.blog, and then you can see GPU in GKA, and then more things. So because we explain here. But this is how I would like to have things. Just a simple file which is code to run. And that's the only thing that I will modify. The rest should be can you see it? Because I see some faces. Let me put the zoom a little bit more. But enough? Yes. You see, that is the important one. That is the code to run. See, the one that we have. And as I told you, what we put is we control the number of epochs that we do. Clear? Then normally I pushed, but here I cannot. So what I would like to do is the same. So pipeline will be launched after pushing. You see, I have divided into two. One will be test, CPU, and deploy into GPU. Spending because so the first thing is asking is for GitLab runner, okay? Yes, the characters are really fuzzy, but it should be points, but this is for the computer. We can have another one. But you see what you have seen there is the testing. So our model was tested on the CPU. Oh, and it was succeeded. Nice. I'm sorry about that. I never think that will be wrong with the code, but you see, so just for you to know, before and then I give time because the other part, because you have to go to Google Cloud, create the GPU cluster, and then deploy the computer. So it takes around 5-7 minutes. Okay, then we can explain you in the meantime. So there, what we have done, we have our code. We put it onto a runner, which I told you, is just a server with a small CPU, only a small amount of memory, and then you can run things. And then what we did is to put there an image. So we Dockerized our environment here. So if you see here, what it's asking is for, it's not here? Yes, here, TensorFlow. You see, I took directly an image from TensorFlow. If you have played with these games, or with this model, sorry, then what you do here is you have installed everything. So TensorFlow, you have installed, not the drivers, because this is for CPU. So you can run TensorFlow on CPUs, and then you have an image of it. You can go there, and then I use the same exact version that we will see in the GPU. Okay, and then here the only thing that we did is just pushing, and then you see we control the number of epochs that we would like to do. So only one, because the only thing I want to see if it's working. That should be shown here, but you are not seeing it. Maybe, do you mind if I put my computer? Yes, it will be 5 minutes, and then we can leave time to the other part. Yes, because you can see it. Also, another thing is that to keep record of everything that you have done, which is really nice. You can see here the pipelines, okay? This is the one that we ran. And now you can see far more better. Oh my goodness. Sorry for that. It's just, I don't know why. The symbols went away. You see that? What I will do normally. Check that the loss is getting smaller, whereas the accuracy is increasing. That's what your deep learning model should do. And here, you're doing that in a CPU, so really cheap. You don't have to pay for this. It's probably your computer or something small. But you're seeing really that your model is working. That's the best point of testing. Here you are testing your model, and then you see if it's really working. Really cool. And you run only from one epoch, so it only took 23 seconds. So see what we have done in 23 seconds. We put an environment where your code is running, and it's run in 23 seconds to check if your work is going well. 23 seconds. Cool, Yes and no. So you have the small answer and the, and the rest answer. This is just for showing. Yes, we really do test, but yeah, this is just for show off. I don't. But yes, so you can do two things. What I will do if I were responsible of this. First, test your code itself. So for any kind of typos and so on. So really, or if you want to test. But this is a really nice test. Nobody's doing. It's cheap. It's testing your code in CPUs. Why nobody's doing? And I will tell you why. It's because to your code to work in a CPU, you have to install TensorFlow and everything, but you say, hey, if I'm going to do deep learning, I'm not going to work in a CPU. I want to work in a GPU, come on. But this is really nice to test as I told you, not only that your model is working, but also that, not only that your model has no typos and no problems, but also that your accuracy is increasing, which is really important in this phase. So yes, we have to wait a little bit. This is a little bit longer, but here it's a little bit more complicated, because here, if you see, let me go step by step. What you are seeing here is we need to install kubectl in order to control a Kubernetes cluster. That's a program. It's installed automatically. And then we check that we have a right version. Here, what we're doing is to connect. And it's also something really nice from GitLab. Your secrets are only kept in one place, in GitLab. GitLab converts them into environmental variables, and then are passed through your runners. So your code is only written in one place, the GitLab. The rest is passed through or via environmental variables, keeping your codes and your password secured and more. Then what we do is to pass our passwords. We pass our different programs, and then we check that we have the credentials for this. It's perfect, so we can join, we can log into our Google Cloud account. Oh, an error. No. That is just because, just to avoid, because we are putting a name here. Then what we check is that if the cluster was generated and in a step before, please delete it. And then that's the reason. It's telling you, no, I don't have this cluster already created. It's just a safe measure. Otherwise, you cannot create a new cluster. That's it. Now here is where you have created the cluster. Here you created it automatically. Then yes, with one command. And in a question of minutes, you have a new cluster with your IP, and yes, I only put one because I have one GPU, and number of nodes, and it's running. Come on, this is so cool. I really like it from all of them. But you see, it's really fast. And don't worry about these IPs. I don't care if you can make a picture if you want, because they will be deleted afterwards, so no problem. But you see, here we have generated a complete cluster in Google Cloud. And with GPUs. One command. And we have access to it. If you see here, what we do here is to get credentials. So not only we have generated automatically the cluster, but we get credentials from it, for it. Super cool, because then we don't have to look into which is the password, the keys. No way, get credentials already configured. And now we check that we have, or we can control the cluster itself. We see that, yes, we can control it. Perfect. Now, what we create is some secrets. That's this part. I will attend here a little bit because I think it's really nice to know from Kubernetes. As always, we always have passwords. Always. In this case, it's because I need a Docker registry, to push my images. In this case, it's Docker Hub. Not so important, but it's my password. I don't want anyone to mess with my Docker Hub account. Then, here, what we pass through is the password itself, and then now it's an environmental variable that we can use here in this command. And then here what I do is the same, but in Kubernetes it's something similar, where you create our secrets. Then the secrets are stored in an encrypted part of the cluster, but you only have to put it once, and one actually in the master node of the cluster. You don't need anywhere else. So also there are control and tightly control, and tightly the access is controlled and so on. Then what we do is, and this is really important in my humble opinion, the code. Because at the end, what I have used is an image from Docker Hub. You will see in the next that we're going to create our own image. But the question is, should I put my code in the image that will go maybe in Docker Hub? That will be a security problem for sure. because at the end my code will be exposed completely, because if you can get the image from Docker Hub, you can get my code. No way. That is not the way. So what we do actually is to build images only with the software that is needed and free, and you can download everything, but our code is passed as a config map, which is it's not so secret, so you can't get it from Kubernetes, but it's controlled. So the only place where my code is here in my repository and in the Kubernetes cluster, nothing in the middle. And then in this way you control who has access to your code. So it's a very nice way to complete. This is where also the magic is working, because we need the drivers. Remember that I started with the drivers are a pain in the ass. Not anymore. One line of code, Kubernetes solves the rest for you. Unbelievable. That is really the magic. So because NVIDIA is really supporting now Kubernetes, only with one line of code, all your nodes are, if they have GPUs, automatically configured. All of them. And if you put more, since this is a demo set, I don't want to get there, but automatically, any server that you put in your cluster, this command will be run. And then you will always get your GPUs updated automatically. So the only thing you have to do if you want to scale this is to put new virtual machines, and then automatically all of them will be configured with the GPU drivers. And here, then you are creating, this is the job, so where your work is going to work. And then here, what we're doing, I hope that is almost finished. Yes, it's finished. So you have seen, I have wait, or the program have wait until your code has run. Then when the code has run, you can see here, job in progress, and then true. Now, first I check that I have access to my, oh, yes, sorry. It moved, it has finished. Yes. Yes, it is. So I have access to my NVIDIA thing. So I don't think that you have this at home, because it's a B1000, I think. So really a powerful machine. And you see drivers. CUDA installed. They are installed. I have created this seconds ago, so 1 minute ago. Oh, actually 15 minutes, but yeah, it's fine. Okay, drivers installed. Come on, guys. That's so nice. And then, yes, I have to download the dataset from the internet. That's it. And then you run your model. But now you're running a GPU. And now we're running all these epochs. All of them. And you can see that our model is working perfectly fine. The loss is minimized as the accuracy is increased. Perfect. And not only that, that's also something really important. Deletion is automated. Now the server is gone. I have my results, but I don't pay any more. I just pay just the amount that I need for running my models, not more Google Cloud taxes. And this is done whenever it's finished. So it's programmed to finish whenever it's finished. One day, imagine that you run 2 days work program that you don't have to control, or maybe it's weekend. With this, you don't need it. Yes, I would like to stop a little bit because it's only, but the other one I will run it. The other one I will see you. I will show you the results directly because it's really time consuming. Questions so far before we go for the complex one? Yes. Yes, you don't need hundreds of Kubernetes. You need only one Kubernetes cluster, and then Kubernetes, what will do for you is to run, this is a job, it's called. You can run several jobs with different parameters. Yeah. Yes, the only thing that you need is to create a cluster with several GPUs, and then Kubernetes will know that, and then will run in parallel all of them. each of them in one GPU, or depending on how you want to configure your cluster, maybe you want to configure 2 GPUs per cluster, I don't know that. But also if you have 2 GPUs in the same cluster, also can run in parallel. Yes, no problems. Yes. Yeah. Yes. This part is automated in this way. So Kubernetes is platform agnostic, but there is one thing that is not scalable, is how do you access to your Kubernetes cluster. My point is that, might know you are building an application and you want people to access your application. Then you have to check with all of them, because you need a load balancer. You need a way to access to your Kubernetes cluster. That is not so easy. Then you have to go for each of them and looking how they do it. But it's just a command, finally. I have to do it for Azure and for Google Cloud, and it's just an additional command that gives you the IP. That's it. Actually, we did that in another project. We automate it, and then we get the IP automatically, and then we can log in without any problem, and then you can test it. Yes? Yes?
Normally you would just have a Kubernetes cluster already running, right?
Yes.
And then you would just, deploy your containers there.
Depending on in which stage of your model are. So my point is that, yes, you are developing your model, for sure. I don't want to wait to create the cluster, delete it. Come on. Then, but the only thing you have to do here is to comment the deletion part. The rest is automated. And maybe you delete the cluster at the beginning as well, so delete a couple of things, and then run directly onto the Google onto the cluster. Yes, yes. Actually, in the block, if you go to the block, you will see in a computer that we have there. And yes, there we have a Kubernetes cluster. So there, it is always running. So that is not we don't have to create it. Also, you have the code there if you want to use your own computer. Versioning. Imagine that, I don't know, I have 2 versions of my model. You can run them as well. You can put one GPU cluster or in parallel working on different versions of my model. So if the second one is faster, I will know. It's more accurate. Not only parameters, also versions of your code. Everything automated. Let's complicate it a little bit more. Who is so brave is a question. That is using Keras. Okay, do you know Keras? Everyone know Keras or TensorFlow? This is Keras. With R. Nobody. Nobody's so brave. Come on. No? Okay. The point is that I will never do that. Or depending on. And if you have really a pipeline that only runs in R, it's fine. But no, if not, I will use Python in any case. But Keras is there, and you can use Python. But what I will show you is what happens when I have my own image. Okay? Oops. Oops. So my question is, what happens if I have, so I have to use, no, yes, of course. And this is the last thing, so I will go really fast, and then we can proceed with the next. What happens when you have one code, but you need additional libraries? So that is a classical situation. You can only, if you only have TensorFlow, it's fine, but maybe you need Keras, although under TensorFlow, there is a version of Keras. So Keras grab some fine, but imagine that you want the last version of Keras. I don't know, or you want a library because part of an ATL process needs some libraries that you have. This is the classical situation. You have to modify your original image. So you have to put things there. Then in this case, we're going to recreate the situation, which is more normal than you expect at the end. We are going to install R on a Keras TensorFlow, the same image that we have used before. We're going to install R, and we're going to install Keras. And then we're going to do it, or we have done it in such a way that we only keep one Docker file. which is, as I told you, is the description for the creation of the image. The only thing that we change is the image that you start. So because for CPU you need this TensorFlow image, and for GPUs you need this, which is from NVIDIA. The rest is automated. So you don't have to maintain 2 Docker files. With one is enough. That means that everything that is installed in the CPU version will be installed at the same time in the GPU version of TensorFlow. That is really cool because then you can test your code. Okay, let me not run this. Okay, I will go directly into the one that ran, and also I save that it is not working. Oh, sorry. Yes. Okay, do you understand the problem? I need libraries in my images. That's the point. So I have to install a lot of things there. Let me put a little bit more of zoom, and you can see it. I check the Docker, works, everything fine. And also, I log in to Docker, because at the end, when I generate these images, they need to be in some registry in order to be accessible for Kubernetes to work. Because I remind you that we generate the Docker images, then we put it on Docker Hub, and then our Kubernetes cluster can get them. So I need to log in into my Docker Hub account. You see here I'm generating the TensorFlow R, which is based on this image. This is the one that we used before, so it's TensorFlow. But then I'm installing things. R. Installed. All the dependencies. If you like R, this is the way to install Keras. Also, Keras is installed on R automatically. Build. Same Docker file, and then it's pushed. Here, what you do is to push into the registry. If you don't know that, Docker images are like zip files. It's like you have a GitHub. You can push and pull. It's similar. It's the same. Then we pull. Okay, perfect. This is for caching it. And here, you see the difference. It's the same TensorFlow, okay? It's the same version. The version of 18 is for because NVIDIA. But the real version of TensorFlow is the 10. The 18 is for NVIDIA. The 10 is the one that is used. So exactly the same TensorFlow version, but designed by NVIDIA for GPUs. And we install exactly the same things. Everything is exactly the same. We push, everything worked. Okay, let's go for the next. And this is exactly the same. Test. You have seen it. I don't have to go there. But this is R. So nobody is so brave as me that can care as in R. Yes, I know. But sometimes might be useful. R, running Keras. Trained, CPU, we're happy because we see that the accuracy is increasing, the loss is decreasing, perfect. Test it. And the final step. Same as before. That is similar. So I won't go through all of this. But you can see that it's the same. And it ran in 12 minutes as the other one. Creating the cluster and deleting the cluster. Cool, I really like it. But my humble opinion, what is the message to go home? Everything is automated. everything. So the only thing you have to really change is your code. If you have a different code, you put there, and the rest of the pipeline is launched as you push in the repository. One final slide, and I promise you that I'm finished. So what do you want to do next? AWS and Azure, but no problem. There, the only thing that will change is how we generate the GPU cluster. That's it. Instead of gcloud, we will use AZ or the AWS AZ. So no problems. There, all of them, they have automated how do you want to deploy your things. So I don't think that it will be a problem at all. And, but this is our next goal, really. Go for parallel, not with one GPU, but with several GPU, how we parallelize. And this is really hard. This is, in my opinion, the next thing for the next 5 years, parallelization of GPU computations. Finished. Questions so far? Yes, more questions. Yeah, shoot.
I was wondering if you already saw like clients, or you advise clients to set up their integration for machine learning or deep learning in this kind of way, or?
Yes, not with GPUs.
Yeah.
GPUs is something that is getting into the market, but slowly. So far, but this kind of pipelines, yes, we have several clients with this already implemented. And then it's the same. The only problem, or the only thing that you have there is your code, and then your code runs, and then get the models are trained, and so on. Or they have, for example, PDF generations, automated, completely automated. Then the jobs is run, the PDF are generated, are sent to the email. Everything automated in the same pipeline. Yeah, we have several of them.
One more, because now it's like quite a small data set, right?
Yes.
Like, images in a really small model.
Yes.
But yeah, also work a little bit with deep learning, and then could be like even one heap could take like maybe 10, 20 minutes to do it. Right?
Yes.
So would you like if you do that in production, would you just take a sample of images just to
test it in CPU?
Yeah, okay.
Yes. So you can do both. So you can do reduce number of epochs for testing, and also, as you say, sampling the data. Then you have a small data set which will be used for testing. And then, in this case, what I will do is to prepare the Kubernetes cluster, not create it and delete it. It has no sense if you are going to put data there. And then you can use the Kubernetes cluster to put the data there. Even you can, we have done it. Also, it's not publicity. I also have another blog about Spark and HDFS in Kubernetes. So you can deploy even HDFS in Kubernetes. And then you can have a massive data set without any problem. And then you can run this on selected nodes, and they have the GPUs. Yes. Yes.
Just let me see if I got it right. When you push, do you push just configuration file, or do you push the sort of like image container itself?
Yes, you can change whatever you want. You can change or the code itself, okay, to change the code to run file, or you change the Docker file. In this Docker file, you have, as you said, the configuration and the package that you want to install. So you build your own images, which they are going to be deployed into your Kubernetes cluster. And everything that is there is configured, even with passwords in the secure way, and credentials, whatever you need.
And then where does Docker Hub, the Docker Hub you mentioned,
yes,
where does it come in?
Yes, for the images, because
the images.
Yes, let me show you here. Maybe I step a little bit, not to bore you, but once, if you see here, what we have done in the runners is to generate these images, but they should be available for Kubernetes in order to run. Then you have to put it in somewhere. What I will do in production, now going for Docker Hub, of course, you can have private registries, which needs a password and so on. And for this example, it's nice if you have. But yes, so the registries is a place, imagine like some space where you can put your images, and then they are accessible to your Kubernetes cluster.
Are you familiar with Java?
Yeah.
It's like Nexus.
All right.
You can have public and private artifacts. Yeah.
Yes. Oh, sorry. Was there a question before?
Yeah. Okay, right. So you built this workflow.
Yes.
You have a way to train your model and test it.
Yes.
It's of course useful if you want to test again and again, right? So like every 2 months you have new input data, so you retrain your model.
Yeah.
Then one problem you have now is that you would have like versions of your models.
Yes.
And you would like to also like be able to deploy them in reliable version plane. So how do you solve that?
Yes. First, you can, instead of jobs, what Kubernetes has is cron jobs, like cron. So you can automate also when do you want to run your models. That's what I will do first. So automate every month. Please retrain my model. Perfect. Already done. Now, you can't move information because from your Kubernetes cluster, and then you have there, because at the end you save one file with all the parameters, and then you can get this into a folder which can be shared, and then you can get access to your parameters, and then you can do whatever you want with them.
Yeah, that sounds like an inferior solution to the really nice workflow you just built, right? Because you have all Git-based versions.
If you don't
deal with your model, but
yes,
the fact that your training, what you set the model, you put in a folder and you give it the name of September 2019.
No, there are more advanced. There are more advanced repositories where you can track that. For example, like Sacred is a solution for doing that. And you can also, of course, after you serialize your weights, you can put that back in the repository. Yeah.
yes.
That's the goal in the end with your mining.
I describe it as a simple version, but at the end you can do whatever you want with your parameters. It's just a file at the end, so you can move it freely, and then you can make a registry with all of them. Even you can check them. You can check that the accuracy that you get is enough, and then it can be sent to your email automatically. No problem. It's just a question of putting more libraries in your images and automate these steps. That's it. Yes.
Do I understand correctly that you have a generic Docker image that sort of clones your source code basically once it's running under Kubernetes? Is that correct?
It's not mine. It's a pity. It's designed by TensorFlow.
Yeah.
So, and the other one is the GPU one is designed by NVIDIA. But yes, they are freely available on Docker Hub.
Yeah. Okay.
Both of them. What only thing I did is in this step is to add things to them. But the original TensorFlow images are freely available. It's free. NVIDIA and TensorFlow themselves, they build also these images regularly. All the versions that you have already are Dockerized almost immediately. Docker is really pushing this industry forward. So even I have seen software that they don't only give you the code, a GitHub repository, but also they give you an image, a link to the Docker Hub, where is the image and the environment that you should have to run the code itself. So far, so good? Yes? How that will be interesting.
So thanks, Angel. Let's just take 2 minutes break. Just go to the bathroom or grab a drink, and then we're going to continue with the second presentation.
So my name is Pratyush Kumar Sinha. I lead the machine learning practice for Infosys in Europe. And this presentation is going to be about unlabeled learning. In other words, it could be called self-supervised learning. So what is unlabeled learning? What is in general, what is unsupervised learning? And what it means is that basically all the data that you have, for example, images. So those images would reside on a manifold, and manifold will look something like this structure. Basically they are color-coded to explain the concept of labels, but if you would not color-code them, they will all look like in monocolor like this, okay? So that's the manifold, and what you want to learn is that manifold. And the best way to do it is to learn the distribution of that data. And in general, every algorithm that learns the distribution of the data, they basically follow that algorithm. You define a distribution, then you initialize its parameters, and then you run this step k number of times. You could decide on the limit of k, but in that step, basically you update your parameters of the distribution, trying to always reduce your entropy of your distribution. And entropy means that the information content in that distribution. You don't want to learn distribution about a data which is like just random flat. It's not useful. You want to learn multimodal, high peak data from which you could sample, take decisions. So where the information content is basically more, not less. To reduce variance, so if your distribution is normal, then yes, but there are many more dimensions like skewness, kurtosis, other moments. So, so basically, when you put these colors, you could see that once you have learned the structure of the data, you simply need a very thin layer of labels on top of it, which will learn these partitions. And it would say that if the data is in that partition, then there's an image of a man looking in, upwards. If it's in that partition, then looking downwards, otherwise front, otherwise left. So that's the general space. So once you have learned this representation of the data, you could do anything on top of that. With very simple, with very less number of labels, you could get your tasks done. And normally with companies, the problem is that we don't focus on this kind of problem solving. We always focus on let's get labels and let's try to solve the conditional distribution, of those labels. What is the probability of that label given that this is my data? Not every time the data is available. Like the labels are not available, and it's a very, very expensive task. Like mostly a real life, like the world wouldn't be Kaggle competition. So it's in our interest to learn that distribution. Now, these are some popular methods of unsupervised learning. What they essentially do is that they learn some aggregate property of the data in terms of these parameters. Normally, I could say that they learn distribution of the data, but in k-means, it really seems an insult to latent variable models to say that it learns parameters of the data. Like it's that simple. So that's the objective function that k-means algorithm tries to optimize. And you could replace that, like in the previous slide, there you could see I've written that always try to reduce the entropy. And that's what that function does. It's kind of an approximation for entropy in this distribution. So probably all of you are aware of k-means algorithm, right? So I'll just skip it. It can be used for like all of these things. It could be used for document classification. You could see I've written that what kind of inputs you need to give. Again, for customer segmentation, you could use recharge SMS data usage. For fraud detection, you could use that. For ride analysis, you could use latitude, longitude, and base. Clearly, there are limitations of this algorithm. you first need to know number of modes, the K, and then it assumes that the distribution around all the known means is the same. That's what its assumption is. And unfortunately, if that's not true, it will get very weird clusters. In other words, K-means is a great algorithm if you believe that your distribution are spherical around all the mean points. Okay? So this is another method called dbScan. Are you guys aware of dbScan? So this is actually the most popular and powerful clustering algorithm. Its objective function is the same, except there you see that that's a Frobenius norm. Are you guys aware of Frobenius norm? It's if it's a vector, there's another vector. You subtract, you take a square, you take under root. So basically square distance. That's called Frobenius norm. So that was the function in k-means. In dbScan, you have a density function. All right. This density function is the key thing that they have defined this. What they do is that it's parameterized by a radial distance around every point, and they count the number of points in that radial distance. And if it meets that minimum number of points, what are the hyperparameters? Then they say that this is a good core point. I should populate my core point dictionary. Then I should go around all the points near that core dictionary and try to see if there are more core points in my neighborhood. Most probably they wouldn't find. But if they do find, they repopulate and they keep on doing it. So this is like, it's a two-level iteration, and that's why its complexity to learn is 4 into the power square. And you can see the difference. It's the same function here. So you would say that then why is complexity O n? Why it's not 1 square here? Because those K are number of clusters. Here there are number of cores, and each core means every point. So literally it has to go through all the point every time. But it's very powerful because it basically doesn't have to assume that your distribution is similar around those points, as you can see. But its limitation is that it assumes that this radial distance is same for all distribution, which might not be the case. So it has its own limitation. Then comes mean shift. Are you guys aware of mean shift algorithm?
An question is can, but like, what do you use as an evaluation for what's 9-point improvements or like some heuristics?
Yeah.
Maybe the idea.
So it's basically convergence. It's there's a density function, which actually calculates density around all the core points. Once it's not moving, and you say have converged. And actually, I just want to explain why all of this will converge is because there is a mathematical proof that these are all kernel functions. So you could always calculate the expectation of your kernel through its own framework, and you will find they all converge. Yeah, yeah. So. Yeah. Yeah. So that's true in all cases. Unless you have an analytical solution, you will get local minimum. Yeah, there is absolutely no guarantee. It's guaranteed that they will converge, but is it a local minimum or global minimum? Is there a better solution than those set of core points? Is there a better cluster than what I've identified? We don't know. It's just guaranteed that there are good ones. They do explain the cluster, but are the best ones? No. There is no guarantee of that. That's mean shift. Anybody know mean shift? It's just another way of how do you update your parameters. Here, when your kernel function moves, it tries to move in the direction, basically, where it finds more core points, like more dense points. Here, it basically moves by finding where is which point is the closest to the mean in that circle, and then whichever point is closest, it just shifts to that direction. So it's just mean shift, and that is like counting density. Rest of them is the same. I mentioned it's parameterized by radial distance. This is a very interesting clustering method. Are you guys aware of Gaussian mean methods? So there's one, he's aware. Anybody else? So 2, 3, 4. Well, okay. So that will be easy. So the objective function, as you can see, is a weighted sum of normal distributions, right? And that's what, if your data looks like, then basically you would use this algorithm that we discussed. You will iterate over k times to optimize parameters, to reduce entropy. And this weight that you see, pi c, is actually the first step of measuring this aggregate score, that how much of each point should be attributed to all these clusters. That is calculated. Then in the next step of your expectation maximization, you try to learn parameters by analytical method. You actually take derivative of that function and you get an absolute mean value and covariance matrix, which you will update in every step. This is not basically, you have analytical solution of what is the best parameter if you know your weights, okay? So every time you calculate your weights by a given function, then you update your parameters and you keep on doing it till you converge. In the end, you can represent your entire data with a set of normal distribution whose mean are known, whose covariance matrices are known, and the weights are known, right? Again, they're the same application. This is a special kind of model because this is a latent variable model. Okay, what it means is this. You know, like we discussed this, but did you guys notice what is there on the x and y axis? Why does it look like this? Why not some other shape? So if you have a high dimension, sorry? Yeah, like, but it's not just that. You could take any high dimension vector, divide it in any way, and try to put it like that. Yes, there's just a conceptual representation that, for example, if it's an image, so it'll be 784 length vector, you could cut it into like 100 here, put rest 684 there. It would still look something like this. So in general, you keep on plotting all the points. It will lie on a sort of shape. You have to learn that distribution. So these are like feature subset. That's why it looks like this. So these are general application in companies. But if you have like 10 gold examples, you have some customer, you can see which customer they are closest to based on these clustering algorithms. So and you will take the same action that you would take on those gold examples. For example, if your query said, I want a taxi ride to airport, you have a gold example saying that I need traveling services to airport. And you cluster and you say, well, okay, I have to order a taxi for this guy because it looks similar to this gold example where I ordered a taxi for him before. That's what you can do. Then it facilitates knowledge discovery. You were mentioning that you were working like in the product discovery, like what's the best product for the companies to market? One of the
best product.
Yeah, like.
Well, they have a number of products, but for example, some medications, cold and flu medications, or
yeah. And like, if you've done like A/B testing, saying that in your repository A these products work, and in B these products don't work. If you have a new product, you run your simple Euclidean match after your clustering. You say, well, I have more match with what works, so this is going to work. Like, you could run your hacks once you have done your unsupervised learning. This is another very popular technique. I think everybody knows about single value decomposition, right? So just to summarize, that's why it's so short, but I'm sure everybody will know about it. Every matrix, every data grid, can be broken down into 3 matrix multiplication. And so that is one example of a random data grid. What it represents is those faces. So every face there is a row, and its features, the eyes, nose, pixel values of the columns. I'm not elaborated on 784, but you can imagine. You can break it down into 3 matrices, and individually they are called basically U, diagonal matrix, and V transpose. That's what the names are.
And what they represent are these latent dimensions. If you break down your data into, then it's really factorizable. You can multiply these elements and recover the actual input. So basically, the latent dimensions from all these faces that we have discovered on B transpose are those 16 faces. I just represent 3, but each one of the row will be one of the latent representations of that data set. So that entire data set could be represented with these 16 images. You just need to make some modification as to what feature is important, and you will recover it. And that you could do for any kind of data, not just, if it works on images, it could work on anything. And its applications are, you could reduce dimensionality because in the diagonal matrix, each one of them, the diagonal is the importance of these latent spaces. So you could choose how much importance do you want to work with. If you have 100 dimension, you want to work with 50, get rid of the bottom 50 eigenvalues, that's fine. Then it's very useful for recommendation system because once you can represent every data based on latent variables, then you can simply give a match. Non-negative matrix factorization is another example of it, and PCA is another example of it. Principal component analysis, yeah. So let's get to interesting stuff. So, like, this is all pretty standard before this. Now, because of, like, how many of you guys work in neural networks? Okay, cool. So, basically, neural network in general is a function. It's just a mathematical function. Like that's the way to see it. It's parameterized by some values, but it's a function. It's a mathematical function that takes something, that does something. It's a mapping. Could be ejective, could be bijective, could be really something random, but it's a function. So variational autoencoder is a way to model probabilistic model using neural network. So autoencoder was the first architecture. What it does is that it takes images, it compresses them to, for example, it will take an MNIST data set, which is of 28 into 28 size, flatten it, becomes 784. Then you compress it to, let's say, a dimension of 100, right? Once you press it to 100, you try to recover the actual data back. Your loss function is a reconstruction loss, right? Reconstruction loss is like simple Frobenius norm. You take the Euclidean distance, you try to subtract, you try to square, you try to recover. That doesn't work very well. That doesn't work very well because what that shows is that because it's deterministic mapping, it's going to take an image like that, pass it through some function, which I call encoder. You could use convolution net, you could use multi-layer perceptron, you could use transformer architecture, you could use LSTM, anything you could use there. From there, in normal autoencoder, you will map it to a compressed state. Now, each data will match to one compressed state, and you will recover the true state from that compressed state. So it's one-to-one mapping. It's not useful. I mean, clustering won't work very well there. Because if like every data set that you have in your distribution maps to one random point, how would you do clustering? You need to know some kind of distribution, some kind of mode around which the data clusters so that you could say that this is my gold example, right? Right? So what these guys did, and actually this was invented by an Amsterdam researcher at University of Amsterdam. This is, and I'm sure this model is going to get like Test of Time award at NeurIPS. It was so good. So what this does is that instead of mapping it to a compressed state, it maps it to the distribution, like literally distribution of, we studied a mixture of Gaussian, right? This is what it is. It maps it to parameter of a Gaussian distribution. That's the schematic representation. This is the mathematical representation where you could see that this, the probability of a hidden state or a compressed state given with data are those basically distribution. Once you have this, you sample from it and you recover the actual image back. That's called decoder. It's called decoder because you're decoding the aggregate hidden complex state into the actual representable image. And it's called encoder because you're encoding it to this complex distribution. Uh, then the reconstruction loss is one of the objective. Another interesting thing that they introduced was that when you are learning that distribution, you have to make sure that the divergence between what you are learning and the actual normal distribution stays, because you're assuming that your prior are normal. So you add a regularizer to your objective function of reconstruction. It's called KL divergence. And you don't have to do much. If you know scale divergence, just slap a PyTorch loss to it, and it will optimize. The only thing you have to understand is that, what is your prior and how do you, write it in tensor format. And it will work. The trick is that, so this is a question for people who work with neural network. So normally when you're coding a feed-forward function, it's all continuous, right? You have an input, you multiply it with a matrix, which is scaling rotation, you take a nonlinearity, you keep on doing it, and finally you have some distribution that you want to map to. But there you have this distribution parameters, and from there you sample. Now sampling is not a continuous operation. How are you going to take backprop? So what do you guys think? People who work with neural network. Backprop only works on continuous functions, right? But in this model, you take your data, you map it to some parameter, from there you try to sample it, but sampling is not a continuous operation. So how do you do it? So that's called a reparameterization trick. What they do is that there is a jump between this and this. This is a Z variable, this is a Z variable, they jump. When you jump, you can't do backpropagation, but in this case you can. What they do is they represent every variable as a simple sum of mean plus variance multiplied by a white noise, epsilon. And they backprop through these parameters, not through the noise. It's genius. Jeffrey Hinton, actually one of the forefathers of deep learning, he said that, I don't understand why it works so well. So everybody should give it a shot, because this I have tried. It's a very powerful financial modeling tool. Anybody who trades in stock market, has got access to some data, should use this model to see what happens. I guarantee you'll be surprised. Sorry? Yes. Yeah, you have to. So, but the thing is, in the neural net, like, how much would you like? You could go from 100 to 5,000. Then you have, it's actually over-parameterized. You have to put regularizers to, further control your, like, probably you would use something not to have 100 parameters. But yeah. But the model that I have tried is not actually many. I have just compressed it to one state. So they're not like 10 or 20, 100. I put everything like 500 days of stock price into 1 point. And that 1 point could tell you, by being on the left or right side, that is the market going to go up or down for the next. It's really cool. You should try it. The best part about this model is that it allows you to learn disentangled representation. So I'm going to be a little bit philosophical here. There is a free lunch theorem. Do you guys know that? Yeah, yeah. Except the pizza. So what this means is that there is absolutely no representation that you could learn that will do well on every single task. It's impossible. The thing is it? What if I learn a disentangled representation, completely disentangled? For example, I could learn representation of a line which is shown in terms of pixels and say, okay, this line is represented by 10 pixels, all these pixels make a line, I'm happy, whatever operation I'm going to do on some compression of it. But if you could compress it back to only two states, the length of the line and the angle of the line, somehow if you could discover that, anything that you could do with a line, you could do with those two parameters. There's absolutely nothing else you need. So it's possible. We just don't know how. There are a couple of papers. You should read it. But the fundamental idea is to have a controlled overlap between these parameters. Right? So I really think anybody who's using like deep learning should give it a shot and should actually try to improve it. What are the hidden things there? So I always work with symbolic logic. So that's a question I asked myself like 3 years back. And since then, I stopped using any continuous value, even for images. For example, the MNIST that you showed, you use the pixel values, right? And then you have convolutions running and then doing stuff. But even for that, I wouldn't use pixel values. I will first learn an encoding. I will use a pixel value as symbol. And in some cases, I will even use them dynamically. I wouldn't keep a static representation. But it really depends on the problem. But yeah. 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 So basically, normally what happens is the clusters which are very indicative of the prediction of the actual image, they get basically more credit assignment. So gradually the features which are not very present, for example, I don't know, green eyes and you're mapping faces, it will not learn how to map green eyes. That's a feature, right? So basically, if it's not present, it would just not model it. When you will sample from that distribution, you will never get green eyes. It is just not learned. So please do try it. It's super cool. And it's super simple, actually. Then there are GANs. And I'm sure everybody knows about GANs, right? They're magical. So GANs stand for Generative Adversarial Network. This is also a latent space model. You should see what kind of GAN image. Like, does anybody know about GAN? Generative Adversarial Network? You do, right? Like, they are mind-blowing. I mean, the sentences they generate, the images they generate, it's just, now there are models called GAN breeders. You just dump 3 images, it will create a baby of it. They advertise it that stuff, like that, baby of 3 images. And it's mind-blowing. It's super sharp, high resolution. That's the structure. That's the schematic structure. What it does is following. You will give it a bunch of data, like MNIST digit, okay? It will try to sample from it. That is the probabilistic representation. It means that X tilde means being sampled from a distribution represented by Q of X. You will push it to your discriminator. People who have used neural network would know that it's just a function, right? You give it, and it comes as either as 1 or 0. I'll tell which one is 1 or which one is 0. But you have a data set, you sample something from it, you push it to your function, you generate 1. Because that data is good data. Now you sample something from a random noise. You pass it through some function, you send it back to discriminator, and then it says it's 0. So it's like a police and a thief. Police is trying to say that I know what's good and what's bad, and thief is trying to say I'm going to make as good-looking data as possible that you wouldn't be able to differentiate. So this is a minimax game, right? If you want to think about the objective function is, as I said, when you look at the data from the data set, MNIST, model should say 1. When it looks from the data from the random distribution, it should say it's 0. And the one that's producing these fake data points should always push towards producing a 1. Very simple to explain. It's very, very hard to train. Like, there was a gap of 2 years before they understood that they have to put some regularizer before they could do stable training. Everybody should try this. This is another absolutely mind-blowing algorithm. In fact, Jan LeCun, who is another father of deep learning, he said that this is the most advanced thing in machine learning in the last 20 years. It's that powerful. Again, many things are not clear. Because what are you really doing? You are reading from a random number to generate human-like images. It's crazy. Absolutely crazy. But it happens. So you could do your own research and figure out what is going on. And NVIDIA is publishing papers after paper to make it as interpretable as possible. It's a question that everybody is trying to answer. So one way is that you look at all the images that's being generated, which is a very bad idea. But people are trying to define some metrics. Basically, some sort of graphical models which get activated with similar features. So it's like some sort of tracker network which trains in parallel, and they try to see if the same activations are firing. But sorry? Yeah. Yeah. I don't fully understand the question, but there is no established accepted metrics to measure performance. Like in MNIST, it's clear, accuracy. You said accuracy is improving, loss is reducing, you are happy, my model is working on Kubernetes. In GAN, you will only see, well, okay, discriminator is becoming like worse and worse. That's the optimum state of this minimax game. Discriminator completely gets confused. When the model has balanced, then generator is generating as good as data as the actual data set, and discriminator is completely confused. That's optimum state. It will give exactly 0.5 if it has learned to the actual data set, and 0.5 to the fake data set. Okay? You will see that, yes. Sir.
I know that GANs are used for data augmentation.
Sorry, data augmentation? Yes. Yeah.
Any other uses for why they are so useful?
Yeah. Denoising and simulation. For example, in denoising, you could look for papers from NVIDIA and from Apple. They're direct applications. So from Apple, what they've done is that when you take a picture from a camera, there is this depth perception that makes the picture quality bad. What they do is that they put the whole image through a GAN to produce slightly modified version of the image, which looks like the depth perception has been solved. How they do it? They give all the images which are well depth perceived to the discriminator. Discriminator learns to either say it's fake or it's real, and finally generator learns to exactly reproduce a well depth image from a bad depth image. Sorry?
Self-driving cars.
Yes, yes, yes. And actually, NVIDIA, they actually presented it in Europe. It's brilliant, brilliant, brilliant. From the that's one example. Another is like from video, like by looking at a bunch of videos, they basically generated a video game environment. So like a car is just driving, looking at some images. They are recording it, and they're trying to generate the next 5, 10, 15 sequences. And they have it's really a complex model because they are not putting the discriminators just on one image. They're putting it across 15, however it's predicting, and they're using multiple auxiliary loss functions to manage flow and all sorts of tricks. But it works like magic. I mean, you couldn't believe it if you saw it. There are 5 frames, and then everything else, it looks like somebody shot it. But machines just put the pixels together. It's stunning. The thing is, with simulation, you could do that with customer journeys. Really with customer journeys. So basically, the idea of every customer journey is that you shouldn't be just able to predict what's going to happen. What's the point of it? Anyway, it's going to happen. Your idea should be how you can orchestrate a change. If you want to look at example in terms of image or text, if you look at, let's say it's a top of 5, right? But you don't know, it could be 7, it could be 5. You're looking just part of the corner. What can you bring in so that that hat becomes a 5? What can you bring in that hat becomes a 7, right? For that, you have to observe that what is at the middle left part of this hat. If you produce a straight line there, you have produced a 5. If you produce nothing, you have produced a 7. So GANs should be able to create that simulation. You should be able to have a couple of quick customer journeys, should be able to map it, should be able to push it to your conditional generator, and that data which is generated should look like actual data. And then you can have all your data you want, just keep on sampling from it. And the one distribution that looks multimodal. So you asked me that what's the way to check these? One of the ways could be that, that if it's all multimodal, like some limits on the mode, then it shouldn't be degenerate mode. Then you could actually check just by sampling. You sample a lot and you plot the overall statistics. So people are trying all those methods. What's next? Oh, thanks. And I just want to quickly talk about self-supervised learning. Now, that is something that, again, all of you should try. The research was in engineering features, right? Image, text, videos, everywhere the research was happening in engineering features. But then came deep nets. And then you don't have to. You just have a loss function, you have some network, just goes and learns it. But now the research is on the architecture, right? LSTM, convolution net, multi-layer perceptrons, attention, GANs, variational. They're all architectures, right? Loss has not changed. It's still reconstructive loss, margin loss, cross entropy, binary cross entropy. So then Google came up with this idea that let's try to build a structure where we take the input, we hide part of it, and we try to ask the model to discover what was hidden in sentence. So that's the BERT model. It has blown every NLP problem state of the art out of the water. And it's soon going to be into federated learning, which means that Google will train a model, a BERT model, to understand the structure in the data. In your next OS upgrade, that model will be sitting on your phone, a compressed model. Whatever you will type with it, autocorrect, it will put a thin layer of fully connected layer. It will learn from that structure to fit to your behavior. In the next upgrade, that compressed state will be sent to cloud, aggregated, new model learned, reshipped to your phone. So once the structure has been learned from the data, you don't even need about privacy. Just learn aggregate structure, push it to phones, let them learn over the phone. From time to time, collect this information, aggregate, recompute, resend. So thank you again.
Thanks, Pratush. So it's actually interesting that you mentioned GANs, because we have another meetup called Snacks and Hacks, and on the 6th of February we're going to be working with GANs. So it's not no presentations, just actual coding, and actually you're free to join as well if you want. So everyone that wants to sign up can do that. Well, I hope you enjoy the presentations. Yeah, I guess. Yeah, actually we didn't. Someone has questions maybe, or no? Okay. Yeah. Well. Yeah. Thank you again for joining. Feel free to grab a bite or a drink as well and stay and mingle a bit. Dario, would you like to say something as well, or no? Then I guess we're finished. Thanks.